So the next part, we're going to talk about artificial neural network. We're going to answer a set of basic questions on what are artificial neural networks, and the simplest, we're going to use the simplest artificial neural network of Perceptron to illustrate the idea behind a general artificial neural network. And we're going to talk about the networks and some key characteristics, how it's different from others. And we're going to mention why artificial neural network has not been successful until recently. As we mentioned earlier, before deep learning, naive Bayesian and support vector machine has all been shown to beat artificial neural networks in various classification tasks. Okay, so what are artificial neural networks? It's a type of artificial intelligence method inspired by the function mechanisms of human brain. I think we all get that idea already through the news. The AANs are really good at performing pattern recognition, and its power probably cannot be cannot be overestimated in lots of application areas. For example, image processing, computer vision, because the system is very good at gathering features. I think this is one of the major characteristics that differentiate artificial neural networks from other applications. Other machine learning algorithms highly rely on the human engineered features. The system performance is largely dependent on the features themselves. Artificial neural network is able to actually filtering through those features and decide what can be used and to what extent they can be used. So it's definitely a very good approach to machine learning. As I think I mentioned last time, we have a class, a whole course devoted to neural network. So today we only going to actually give intuitions. So to prove or provide evidence to my point that the system learns, artificial neural network learns the features, is when you input to a deep neural network with your pictures, the system will layer by layer and learn different features that can be used eventually for a classification task, whether this picture is a human face or not, for example. It can be shown that the features learned at the beginning of the network, it's lower level features. We see lines, boundaries, and in the middle part we start to see shapes and quite consistently. And in the end part of the layer, often you can actually see the complete faces. In text processing, similar, although they cannot be presented so visually, similar ideas applies. So artificial neural network certainly is widely used for natural language processing as well. So I actually found and included this convolutional neural network picture. I think it's very useful not only to explain that there's lots of parts that devoted to feature learning when we recognizing a character. A convolution network is the one that's often used to recognize, understand images. So they go through a feature learning step to actually abstract from lots of raw pixel-wise data points to different layers of features that actually can be put into a feed-forward neural network that's fully connected, and eventually to a softmax layer that can do the classification. This is important. It's relevant to this class because later on we're going to talk about transfer learning. And neural network is very useful for transfer learning. And we're going to come back to this picture when we get to the point where we talk about transfer learning. So in reality, when we implement artificial neural network, it's just a collection of interconnected neurons. And every neuron perform a very simple function. It receives input from the previous layer and dispatches output to the next layer. But with those every single node performing very simple functions, miracle happens in the end. We're going to use, artificial neural network, you can think of it as, many people say it's a black box because we see the input and output internally. How it works is actually very hard to understand. This has been cited one of the drawbacks for artificial neural network, that it has lower interpretability. So this could be a representation of artificial neural networks, input, output, and connected to a black box. So the attribute values I want to mention here is often normalized for different types of neural networks, often a small number, depending on the activation function used in artificial networks, often in the range of -1 or +1 or 1 and 0. The one that we're going to use today to illustrate the idea is a perceptron. Perceptron is the simplest neural network. It has input nodes and it has output node. So this is considered a one layer neural network. When we can count the layers in the neural network, there is not, well, some people count input layer, but I think at this time, most people would stop counting input nodes as a layer in the network. We only count the output and the hidden layer. In this case, we don't have any hidden layer in between. We only have one output layer. So therefore, it is a one layer network. So what does this network node does? It accepts input and have the arcs link the nodes to the output node. And each arc has a weight on it. It can be initialized to random and then learned by the system. And there is often a bias, but in this case, the original perceptron actually call it threshold. So we have a difficult time with terminology here. Sometimes I call it threshold, sometimes other times bias, and also bias can be treated as weight as well. So it's a little bit confusing. But I guess you can forget about that. Doesn't matter. It's just a part of the things that you need to generate the output. So for this perceptron, the output is generated using a sign function. If the input x is greater or equal to 0, then the sign function is going to return a 1. Otherwise, it's going to return -1. So this is our, in this case, it's activation function. It also output to the y directly. So in general, so we just illustrated one perceptron that we're going to use as our example in this lecture. But in general, you will have, for general artificial neural network, you have input layers with many, many nodes. You can have 1 to many hidden layers with many, many nodes. And you have output layers with certain number of nodes. The most popular number of nodes in the output layer, depending on your prediction problem. For regression or numerical prediction, you will have 1 node in the output layer most often. For classification task, your output layer is going to have as many classes as you have. although there's other configurations possible. So besides the weight, the weight is connecting node to the next node, to next level's nodes. The nodes may not be fully connected depending on the network topography. But the nodes are often indexed by pairs of, weights are often indexed with pairs of the nodes that it's connected. And bias is to the layer. So there is one bias each layer. And every node has taken those input, and it has activation functions, and it has output. So learning a neural network is just trying to learn the weight and the biases that you can you put into the network. The network topology was given or chosen by you, and in terms of how many nodes in every layer is all hyperparameters that you need to decide. So you can think of the topology has been given. The learning is just a task of finding those weights. So this is our perceptron that we're going to use as example. To make these things a little bit easier to read, I have converted this T to a weight. So weight now is starting from 0 to D. I admitted the last T, negative T here as the weight with X0 all being 1. So this is equivalent to using T as a threshold. So the rest of the slides here is to illustrate the process of learning the weights. So in general, in neural network learning, you actually initialize the weights with some random numbers. There has been substantial research on how to initialize the weights for the neural network. But some sort of randomization is definitely involved in there because we actually don't know what would be the best thing. The rest of the process steps is to just adjust the weight so that the weight help us to predict our training examples in a correct way. So once we initialize the weight in the simple neural perceptron for every training example, we compute the output function. And then we found how this output function different from our expected result. If we expected -1, but we didn't get -1, then there is an error. And then we're going to, this is the error. So this is our truth, and this is what we predicted. And the difference is our error. So we're going to adjust our weight by adding a little factors to this weight in order to make our function predicts better the next round. So in general, the artificial neural network have a similar learning function, where the next weight is a function of the initial weight and plus lambda, that's the learning rate, and the error, and the initial input. The general formula is the same, except here we just our function is simpler. So we will do this, update the weight, then we read in another example using the new weight and compute the output and see how this output is different from the given value. We update the weight again until we have completed a certain number of iteration or our performance of the model has reached a certain threshold. And that's when we would stop. I think we already covered this.